All right. So, the metric system. The United States, okay, Liberia, and Myanmar are the only ones who don't use the metric system. And last I read, I think Myanmar started using the metric system more and more. But we are three nations in the whole entire world that don't use the metric system. We still use the archaic English system. The English system makes no sense whatsoever, and the reason science uses the metric system is so that even if we have a language barrier, we can all look at the results and understand it. To me, the metric system makes more sense because it's all on powers of 10. Okay, so there's no more feet and inches and worrying about how many cups and quarts and pints and things like that. It's just being able to move a decimal by a power of 10. The units in the metric system: length is meter, volume is liter, mass is gram, time, hey, we kept the second, temperature is the degrees Celsius, energy, all right, is calorie. We won't worry about that right now until chapter 6. Mole we'll worry about in chapter 3, and amps if we get to electrochemistry in Chem 2. Okay, so we tried to convert to the metric system multiple times. We chose not to. In the late 70s, Jimmy Carter started the metrification of America and got huge resistance and basically gave up on it. And we just kept the English system. However, being American, we kept the metric system where we wanted to, and the English system when we wanted to, even though it's primarily English. But if you think about it, you go to the store and you buy milk, you buy it in a gallon, but if you pick up a bottle of soda, it's in liters. And if we sat there and said, okay, I could buy 2 liters of milk for $2.99 or a gallon of milk for $2.99, the majority of Americans wouldn't understand or figure out which one's the cheapest. They think maybe 2 liters is more or whatever. I see memes all the time about stuff like that. But in our case, we go to the doctor, we weigh ourselves in pounds, all of our medicines in milligrams per kilogram of body weight. So what we're going to need to be able to do is convert within the metric system, all right, to the English system, and the English system to the metric system. All right, you don't have to memorize the conversion factors. When an exam is there, I will upload or send or make available on Blackboard a sheet that has conversions, or I'll include them in the problem itself. So don't memorize conversion factors. All right, but let's start with the metric system. The metric system works all on prefixes. Okay, the prefix tells you how much, and that's why it's great, all right, compared to worrying about inches, feet, and all of that. All right, in science, we're not really going to use, in chemistry, I should say, not mega, giga, and tera. That's more computer science. All right, your micro, nano, pico, and femto, all of those down there, microbiology, things like that. We're going to focus in the kilo and milli. It doesn't mean you don't have to know these, but these here, kilo down to milli, is going to be a lot easier to convert. Now, you want to use math to convert, go right ahead and use math and say, well, if I look at it real quick, a kilo is 1,000, all right, of the whatever base units are. My base units, grams, liters, meters, whatever it is. Okay. And so on. Or we can use what is known as the ladder method. Okay. Now, this works great for kilo down to milli because they all go down by 1 power of 10. So, kilo, hect, dec, or deca, are base, deci, centi, and milli. And it doesn't matter if it's millimeters, milliliters, milligrams, millipizza. The milli tells you what it means. And this is, okay, 10 to the third, 10 to the second, 10 to the first, 10 to the 0, or 1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. If I wanted to do a conversion, and I don't want to do math, and it's within these units here, okay? The rule is if I move down, okay, my decimal moves to the right. And if I move up, my decimal moves to the left, the number of spots I'm moving. So if I had, let's say, 25 grams, and I wanted to know how many milligrams that is, I would move down, and I would count the number of spots. 1, 2, 3 spots. Therefore, my decimal, which is at the end, would move 3 to the right, and we'd be 25,000. Okay. If I wanted to know how many kilograms that is, I would count 1, 2, 3 spots, and my decimal would move 3 to the left because I'm moving up and it would get smaller, or 0.025 as I would move 1, 2, and then another spot we would need that 0 there. Okay. This is known as the ladder method, and to me it's easy if you remember, these in order. Where the ladder method becomes a little bit tricky, and not tricky, but you have to just remember, is when we get down to the bottom here. Okay, after milli, the next one on our list, there is micro. And micro is represented by the Greek letter mu there, and it's 10 to the minus 6th. Okay, unlike these here, from kilo down to milli, that go in order 3, 2, 1, 0, negative 1, negative 2, negative 3, there is no negative 4, there is no negative 5. So if I wanted to use the ladder method and turn my 25,000 milligrams into micrograms, I have to take into account 1, 2, 3 more spots, and it would now be 25 million micrograms. Okay, that's the number one thing. You have to make sure your power. Same thing if I wanted to move up to mega, it's 10 to the 6th. But it's really, I didn't realize my micro is cut off there. There we go. It's really simple at moving it up and down. Okay. So, another thing that happens, and I want to point this out, let's say we had something like 100 meters squared, like so. Okay? And I want to know how many centimeters squared that is. Here's what you have to do if you're going to do the ladder method. Okay, whatever, if I'm dealing with squares, cubes, things like that, so area or volume, so this would be an area, I can't go like this and say 100 meters cubed is, I went down 2 spots, add 2 zeros. This isn't right. 10,000 centimeters squared, that's not right. If it's squared, you have to do the ladder method twice. If it's cubed, you have to do it 3 times. Okay, so I'd go down 1, 2, 3, 4. Do it twice. So therefore, I'd have to add 4 zeros to my 100. So 1, 2, 3, 4, comma there, comma here. And that would be our centimeters squared. Okay, so ladder method works as long as you know there's placeholders in between. And if I'm squared or cubed or something like that, then I have to move I have to do the ladder method however many times my power is. Okay? Now, just so you guys know, all right, and are aware, I'm in a rural area and we have a thunderstorm rolling through right now, so I could lose power. Okay? Which means if I do lose power, I'll just finish the video and upload it at another time. So I'm just letting you know that as the thunder starts shaking my house here. All right, questions on the ladder method or converting within the metric system? Yep, Brittany, so if it was 3, I'd do it 3 times. So let's say we had, we had 3,111 meters cubed. And I wanted to know how many kilometers cubed that is. I would count 1, 2, 3, and I would do it 3 times. So my decimal will move, and this is a comma here, but my decimal will move 3, then 3 more, then 3 more, and I would be left with something like 0. Let's see. Zeros. So 0.123. I think I got it right. 45311. Let's see. 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So that's what I would end up with. I'd end up with something like this. And we'll talk about scientific notation in a little bit and things like that. Actually, totaling to 9, you do it 3 times. Well, depending on where you're moving. If we were moving to centimeters, like the last one, yes, you're right. It would move 6 to the right. Yes, if we were doing like the last one. I used a different example, but yes. So if we were doing that last example and it was meters cubed and we wanted centimeters cubed, we'd go down 1, 2, 3, 4, 5, 6. Yep, that's 1, 2, 3, 4, 5. The decimal 1, 2, 3, 4, 5. Then 3, 1, 1, 1, 1. Because I'd have to move it 9 spots. 1, 2, 3. Then do it again. 4, 5, 6, 7, 8, 9. So the decimal is here to start. 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. Okay. All right. Well, being that we are in America, and like I said, we use the metric system without even realizing we're using the metric system, we have to be able to convert from the metric system to the English system and vice versa. What we're going to use is conversion factors. Now, those of you who have taken chem before or taken it in high school or whatever it is, however you get the conversion and however you're comfortable doing it. Some people like proportions, some people like fractions. I learned with fractions and proportions, but I found over doing this for a while, you guys hate fractions. So there's something called the factor label method, which hides math and fractions, and it's just matching things up and crossing things out. So let's say we had 275 pounds, and I want to know how many kilograms there is. Now, in your book and on the slides, there is a conversion chart that tells you how many pounds are in a kilogram, how many kilograms are in a pound. What I know is that there's 2.205 pounds for every kilogram. Now, again, okay, if you don't like the factor label method, that's fine. Whatever method you are going to be comfortable with, as long as you get the right answer, I don't care. So here's how the factor label method works. Draw a line and make a cross. What you know goes in this first block. What you're given to convert goes in this first block. So we're given 275 pounds. Okay. In the next block should be our conversion factor. Our conversion factor is that there's 2.205 pounds in 1 kilogram. Whatever units are up here that I need to get rid of need to be down on the bottom somewhere to cancel out. Okay, so 2.205 pounds, 1 kilogram. Okay, so if we're looking at the factor label method and we're taking notes on it, these values should be equal to one another. They should be equivalent. This block over here should be what you're given to start. Okay? And then we do the math. Now it's math. I could hide the math for as long as I could, but now we got to do a little bit of math. Okay? First thing, if stuff is on top and bottom or top and bottom, no matter which way, the units cancel out. That's number one. Now, in order to solve this, I'm going to get my calculator out to get exact. You multiply across the top and you divide by the bottom. Multiply across the top. Okay. Multiply across the top. Divide by the bottom. Or you can multiply across the top, multiply across the bottom, and then divide. I think doing that and writing the numbers down every time, that could cause some mistakes. So I like multiplying across the top and dividing by the bottom. So 275 times 1 is 275. Divided by 2.205 equals, I'm getting like 124, 125 approximately as my answer. So my answer is approximately 125 kilograms. Okay. Now the beauty of the factor label method versus, fractions or proportions and things like that is you could do multiple problems, multiple steps in one big thing here. So let's say instead of this, we have a 180-pound person, okay, and they walk into the emergency room, and the medication you need to save their lives, all right, is 3 milligrams of medicine, okay, for every 5 kilograms of body weight. And we need to figure out how much medicine we need to give the patient. And if you ever see doctors in emergency rooms and things, they'll have these little cards on them sometimes that allows them to quickly look up and do the conversion of pounds to kilograms so that they could do the math and give the right medicine. Okay. So, how would we do this problem? Well, I can't figure out the medicine unless I get it to kilograms. So my first step is write down what I know, 180 pounds. Next, okay, I'm going to figure out how many kilograms I have. 2.205 pounds is 1 kilogram. Now, this tells me how many kilograms of body weight I have. All right? But that's not what I want to know. I mean, the patient's laying there, and I look at him and say, sir, you're about 87 kilograms of body weight. Well, that doesn't do anything for the patient. We need to figure out the medicine. Now, if you're doing a proportion, you'd have to set up another proportion, but the factor label method allows you to continue on using, here's our next conversion. I want to figure out how much body weight or how much medicine I'm going to give based on the body weight. Well, I need the body weight to cancel out. So I put that on the bottom, and I put its equivalent, the 3 milligrams I would give as the medicine, on top. Just so you know, Rx is actually a Latin thing, and the X part, that line that makes the X, is really Jupiter's thunderbolt. In case you're ever on Jeopardy, you can give me a shout out if that's a question or something. All right, now we do the math. Okay, I'm going to do it 180 times 3, divide it by 2.205, divide it by 5. If you want to multiply across the top, then multiply across the bottom, then divide, you're fine. Just make sure you don't write the wrong numbers down over here. The other mistake I see is we multiply here, we divide by this, then we hit multiply again. Anything on the bottom, hit your divide symbol. 180 times 3, which is 540, divided by 2.205, divided by 5, and we should give out roughly 49 milligrams of medicine for this patient. Okay. Questions on this so far? We're going to do a couple more. And then you're going to do a ton for homework. Gotta clean my eraser. Anything? Okay, and then let's look at another one. Let's say a car gets 20 kilometers for every 4 liters of gas. And we want to know how many miles per gallon do we get. Oh, we're going to talk about that, Tori. We're going to talk about where we round and things like that. I just don't want to throw that at you just yet. We're going to talk about it at the end of this video. Okay. So let's say I want to convert this. Now, there's 1.609 kilometers is 1 mile. There's 3.785 liters in 1 gallon. Now, I'm going to draw my line, and here's again the beauty of the factor label method. Here's what I know. Now, this line here, it might be a line, it might say the word per, is this line here. So you put the 20 kilometers here, you put the 4 liters down here. Mistakes students make are they try doing something like this and then don't know what to do. Don't do that, okay? Choose which one you want to convert first. Let's convert the kilometers. Okay, so 1.609 kilometers goes on the bottom. 1 mile goes on top. Kilometers cancel out. If I were to stop right now, I'd be in miles per liter. Not what I want. I want miles per gallon. Well, I need the gallons to be on the bottom. I need liters to cancel out. Even though the liters are 2 blocks away, it doesn't matter. They'll still cancel out because one's on top, one's on bottom, and the gallon is on the bottom. Okay? I'm left with miles right now. I'm left with gallons, and that's what I want. Miles per gallon, or MPGs. Do the math. Times 3.785 divided by 1.609 equals, give or take, 11, 12, about 12. And I know people that are going to watch this be like, oh, you're not doing your sig figs right. Well, I'm not on sig figs yet. We will worry about it. I just want you to be able to get the right answer. So essentially, this is almost 12 miles to a gallon. What, a 1996 Jeep Grand Cherokee? All right, not very fuel efficient here. So if you're given something with per or over, you can use that first block to do it. What if I had, squared units or things like that? What if I had, 3 feet squared, and I wanted to know how many centimeters squared that is? Okay, there's 2.54 centimeters in 1 inch. Okay, and we know that 12 inches are in 1 foot. How do we set that up? Now, here's what I suggest you set up so that you don't screw this up, because the common mistake is if I'm going from 1 foot to inches, let's say first. Okay, so what's my path going to be based on my thing? I'm going to have to go from feet squared to inches squared, from inches squared to centimeters squared. And if you need to write out your path before you even start, I suggest doing that until you get comfortable with doing this. 1 foot is 12 inches, but 1 foot squared is not 12 inches squared. You can't say that. I see this all the time on the test. Oh, well, 1 foot is 12 inches, then 1 foot squared must be 12 inches squared. No, 1 foot squared is actually 144 inches. Okay, so here's what I suggest that you do. If you have feet or you have, something squared, cubed, whatever it is, write it out like this. That way it'll remind you to convert it twice. 12 inches is 1 foot. Now it would look ridiculous. I'd be in feet inches. We don't want that. What is a feet inch or a foot inch? 12 inches is 1 foot. Oh, yep, I did it right. Okay, I just want to make sure I did it right. All right, and that would put us in inches squared, but we want centimeters squared, so we continue on. 1 inch is 2.54 centimeters. And I have to do that twice. 1 inch is 2.54 centimeters. Cancel out my inches. Okay, and do the multiplication here. 12 times 12 times 3 times 2.54 times 2.54, and we get 2,787. Okay. Questions on that? Density of an object, okay, is a physical characteristic of the object. Uses metric or English systems. It uses measurements. It's a measurement of mass per volume. Okay. My cursive M's. Everyone always yells at me, why do my M's have 3 humps? Well, in cursive, your M's have 3 humps. Lowercase m's. All right. So density is a measurement of mass per volume. Density is a reason something floats and something sinks. Okay, it doesn't have anything to do with just mass. It's the mass per volume. Okay? The more dense a substance is, it will sink. The less dense a substance it'll float. So anytime you have units of mass per volume, okay, so for solids, it's usually grams per centimeter squared. For liquids, it's usually grams per milliliter. And for gases, all right, it's usually grams per liter. All right, so I'm going to just write solid here because, and then liquid and gas. But any units of mass per volume, pounds per feet cubed, that is a density. Okay? More dense, there's my triple M again. Okay, less dense floats. And there's something known as the density triangle. Okay. M, V, D. If I want to know the mass of a substance, okay, I cover up what you're looking for, take density times volume. If I want to know the density, mass divided by volume, I want to know the volume, mass divided by density. Okay, to do the math. Now, if the object, okay, so I have let's say a wood block. It's a cube, and I want to measure it, and I want to know its density. Okay, what would I do? I'd put the cube wood block on a balance. I'd get its mass. And then I take length times width times height, or essentially side cube, and find the volume and do mass per volume. If I was a liquid, okay, I would get a graduated cylinder, fill it to a certain volume, then weigh the graduated cylinder, and by mass weigh it empty, then weigh it with the liquid and figure out the mass. Gases are a little bit different. We'll talk about how to get the density of those when we talk about gases. But what if I had an object like this? Okay, I had an object that looks like this, and I want to know what its density is. Well, how the heck am I supposed to take its volume? It's not like a cube or a sphere where I can look up the formula. All right, let's say it weighs 2 grams. How am I supposed to take the density? Well, here's how you take the density. Okay, you take a graduated cylinder. All right, and the graduated cylinder is going to have volumes on it, 10 milliliters, 20 milliliters, all right, 30 milliliters, whatever, and so on. And you're going to fill it with water. Now, when you fill a graduated cylinder with water, due to the glass and everything, you're going to get something called the meniscus. And the meniscus, the bottom half of that meniscus is going to tell you where you start. So my initial volume of water is 10 milliliters. You're going to take this object, and as long as the object sinks, is more dense than water, you can do this. If it floats, then it's not going to work. But let's imagine this is a rock that is more dense. We're going to drop it in the water. And there's that weird object in the water. And what it's going to do is cause the water level to rise. Okay? Now, let's say it causes the water level to rise, and the new meniscus is right about there, and we say that that is, I don't know, want to say it's 15 milliliters? Sure. So my final volume is 15 milliliters, which means that the object's volume, the volume of the object, is the difference between the two, is 5 milliliters. Okay? So if I want to find the density of this object, I just did, I have to do the math. 2 grams over 5 milliliters, or 2/5, also 4/10, would be 0.4 grams per milliliter. Okay? 0.4 grams per milliliter. Now, let's see if that density is logical. Let's say we did this in a lab. Here's the result we got. We did the math right. We weighed it out. We dropped it. We did everything. We had the initial volume. We had the final. Okay. The density of water. Okay. Now, densities are dependent on temperature and pressure. But in general, the density of water is about 1 gram per milliliter. Okay. Now, we calculated this rock's density to be 0.4 grams per milliliter. And the density of water is 1 gram per milliliter. We have an issue here. Our results don't match logic. Because if the rock really sank, it should be more dense. More dense sinks. Well, water's 1 and my rock is 0.4. If that were really the case, then this rock would float, not sink. So just because you got data, it doesn't mean it's logical. So when you finally do take the Gen Chem 1 lab, we actually do a lab like this. We use a marble and things like that if you take it with, us at LCCC. But make sure your data is logical. So what's wrong here? Well, this rock can't weigh 2 grams because the math doesn't work out. But what if it weighed and we made a mistake and we missed the 1 and it really weighed 12 grams? Now, does that make sense? Well, let's find out the new density. 12 divided by 5 equals 2.4. Now, that's a logical statement because 2.4 is more dense than 1, and that rock would definitely sink. Okay? So make sure your results make sense, is what I'm basically telling you here. All right, questions on density. There'll be homework problems on this again, just like everything else we're doing, conversions and all of that. There'll be a lot of homework to keep you busy over the weekend. I know you're excited. Let's talk about scientific notation. Taking really big numbers or really small numbers and turning them into scientific notation. So what scientific notation allows you to take bigger numbers and turn them into smaller numbers? In our case, it's not going to make a difference. But here's what you do. Okay, step 1. I'll write our steps down here. Step 1, make a number between 1 and 10. So what I mean by that is move your decimal until you make a number between 1 and 10. 3.12 is between 1 and 10. We assume the decimal is here. 3.12 is a number between 1 and 10. So we got 3.124312. And over here we have 3.12. Okay, so make a number between 1 and 10. Step 2. Multiply by 10. Okay, multiply by 10. Multiply by 10. Step 3. Raise it to the power of the spots you moved. I moved 1, 2, 3, 4, 5, 6 spots. I moved 1, 2, 3, 4, 5 spots over here. Step 4. If the decimal moved to the left, it's a positive. If the decimal moved to the right, it's a negative. Decimal moved to the left, positive power. Decimal moved to the right, negative power. And there we go with scientific notation. This is step 4. So you should be able to convert from scientific notation into whole numbers and from whole numbers into scientific notation. Questions on that? You guys are being quiet, and I can't see your faces to see if they're full of fear or if you really have this. So if you could, relieve my anxiety by letting me know either way in the chat, that'd be awesome. So now we're getting to the part that everyone hates in Chapter 1. And everybody you talk to that ever took a Gen Chem course. Brittany, you'll have a lot of practice with the homework and the sheets up online. Plus, this video will be online. Plus, if you go on Blackboard, I have another person who basically had a whole bunch of, online tutorials. So you can hear it from another perspective. So guys, if you haven't logged on Blackboard and looked at the information that I have up there for you, there's a lot of good information. All right, so to answer Tori's question, where do we round to? How do we know what to round? It all starts with something called sig figs. Everyone hates sig figs. I understand it because it's a bunch of rules you have to memorize and apply, and you guys don't like math to begin with, and you finally get the right answer, and then you don't round it correctly. Okay? So this will be the end of the lecture today and everything when we're done with sig figs. First thing, what the heck is a sig fig? A sig fig is any number that's not 0. Okay, we got to start with being able to number our sig figs. So 311, okay, 115, 321, 3,212, let's say. These are all sig figs. This one has 3 sig figs. This number has 3 sig figs. So being able to say how many sig figs you have, this one has 4 sig figs, okay, is going to be important. So if I'm not 0, I'm considered significant. If I am 0, there's 3 rules, okay? Number 1, if I'm a trap 0, meaning I'm stuck between non-zero digits, I am significant. All right, and if you guys took chem in high school, I'm sure you're having flashbacks now about this. But all I keep hearing from students every year, and I know it's not 100% true, is my chem teacher in high school was terrible. 98% of you guys tell me all of that all the time. And I know it's not true, but hopefully I can ease the flashbacks here. Calm your PTSD. All right, so if I'm a trap 0, I'm significant. If I'm a leading 0, okay, like this, I am not significant. The rule is with decimals, find your first non-zero digit, that one, and everything after is significant. Okay. The last rule is this: if I'm a trailing 0. If I'm a trailing 0, okay, I'm only significant if there's a decimal in the number. It doesn't matter where the decimal is. If there's a decimal in the number, I'm significant. So 300 written this way is 1 sig fig. 300 written this way is 3 sig figs. So if I had a number like this, 0.000301020, and I said to you, how many sig figs? Okay, leading zeros are never. Trap zeros are. These are. So I have 1, 2, 3, 4, 5. And what about this one? Well, this one is 2 because the decimal place is there. Even though it's not at the end, as long as there's a decimal. So again, the rule is, if there's a decimal, find your first non-zero digit. That one and every other number is significant. That one and every other number is significant. So this would have 1, 2, 3, 4, 5, 6 sig figs. Okay. Question on how to tell sig figs. Because now we're going to get into the calculation and the rounding and where should I round to and how many numbers should be in my answer and blah, 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 and so on. So there's two rules. Two rules. Okay. There's the addition-subtraction rule. And there's the multiply. I'm running out of space. Divide rule. Okay. Adding and subtracting, you look at decimal places. Multiplication, division, you look at sig figs. Okay? So, let me explain that. I got three numbers to add up. 33.3, 21.72, and 20.812. And I tell you to add these up. So you would tell me the answer is 3. What do we got? 18, carry the 1, 3, 4, 5, 3, 5, 7. 75.832. Okay? The thing is with sig figs, if I'm adding and subtracting, I could only report to the number of decimal places as the least number of decimal places in my values. So I don't know this value or this value or this value, which means I can't report this. I can't report this column. I could report up to here. Adding and subtracting least number of decimal places as the value with the least number of decimal places. Okay? So I would say it's 75 point, and then I would look at the 8 and the number that comes after. So I know I could report to the 8 what comes after. If this is 5 or greater, okay, hold on to that. If this is 5 and change, so like there's a 5 and then numbers afterwards, or greater, you're going to round up. If it's 4 and below, you're going to keep it the same. So this would be 75.8. Okay, now let's go over here. Multiplication and division does it with the least number of sig figs. So let's say, we'll do an easy one. We'll say we have 32 times 2. Okay? Our answer would be 64. However, with sig figs, your answer has to have the least number of sig figs as the smallest number of sig figs in your values. Meaning, this one has 2 sig figs, this has 1 sig fig. Therefore, when I multiply them together, 64, I have to have 1 sig fig. So my answer would be 60. I would look at this. Okay. I would look at this. This is my 1 sig fig. What number? It's a 4. Keep it at 60. Now, if this was 2.0 and not 2, then we could report it as 64 because there's 2 sig figs and 2 sig figs. So let's look at another example of this. And if I do, let's say, 33.3 times 402, my answer, or let's say 4,021. My answer, whatever that ends up being, has to have 3 sig figs only. Okay? So adding and subtracting, least number of decimal places. Multiplying and dividing, least number of sig figs. But here's the caveat, and Tori, here comes the question to your answer. Where do I round and things like that? The only thing, I'm going to actually look at you. The only thing, okay, that counts towards sig figs are your values, not the conversion. So 1 mile is 1.609 kilometers. The 1 mile doesn't count as a sig fig. It's whatever your conversion or factor that they give you, whatever your measurement is, counts towards sig figs. Do not pay attention to formulas and conversions and things like that. Okay? So focus on the values that they gave you. What if there's multiple steps? What if I have to do a multiplication, a division, and then an addition and a subtraction? Worry about rounding at the end. Number one. Multiplication and division takes priority over everything, just like in PEMDAS. Please excuse my dear Aunt Sally. So this rule will take effect over this rule. Some people will tell you it's the last thing that you do, but usually multiplication and division takes precedent over your adding and subtracting. So worry about sig figs at the end. Okay. One silly rounding rule I have to point out to you guys, and it's based on averages and things like that, is the following. Okay. I have this answer. It's a 5. It's exactly 5. There's no change. It's not 37.51. It's not 37.5. 100 zeros 1. It's just a 5, and I have to round. Let's say I need to put this into 2 sig figs. This would become 38 because it's a 5. Okay? However, if I have 38.5, it stays 38. If the number, now this only happens if it's exactly 5. It may never happen in your life, just so you're aware. But I have to mention it because the book mentions it and it is a rule. It has to be exactly 5, the number that you're looking at to round. If it's an odd number, we round up. If it's an even number, then you keep. So 39.5 becomes 40, but 40.5 stays 40. Okay. It's a silly rule, but it's done because of averages, because 5 and change, 6, 7, 8, 9, you round up. 1, 2, 3, 4, you keep. And then 5, exactly, they say half the, or 0, 1, 2, 3, 4, 5, that's 5. Or 0, 1, 2, 3, 4, that's 5 numbers that you keep. 5, 6, 7, 8, 9, you round up, there's 5. Then half the times this will be an even number, half the times it'll be an odd, so they split it. Let mathematicians get in there and average everything out. That's what happened there. Okay. All right. I forgot one more topic because I'm going off the cuff and not using the slides, but they're all on the slides. So I didn't have to keep stopping back and forth. Do you have questions on sig figs? All right, there's 3 temperature scales that are still used today. Degrees Fahrenheit, we're the only ones that use it. We use it on weather reports. Degrees Celsius, everyone else uses. And there's Kelvin, known as the absolute scale. Because absolute 0, there's no negatives. Absolute 0 is the coldest possible. And at absolute 0, okay, all hell breaks loose. All physics, all those chemical bonds, those interactions we talked about earlier, they start breaking apart. Okay? So we need to be able to convert within degrees Fahrenheit, degrees Celsius, and Kelvin. All right, if I want to find degrees Fahrenheit from Celsius, okay, I take 9/5 my degrees Celsius, and then I add 32. So if you want to put this in brackets, go right ahead. Now, degrees Celsius has two conversions for itself. Degrees Celsius is how you get from Fahrenheit to Kelvin. There is no direct correlation. And so degrees Celsius, I could find it two ways. It's 5/9. Make that a better 9. 5/9 degrees Fahrenheit minus 32. Okay. Or if I want to go towards Kelvin, or use Kelvin, it's Kelvin minus 273.15. If we come down to Kelvin, Kelvin is degrees Celsius plus 273.15. So there is no direct correlation from Fahrenheit to degrees Celsius to Kelvin. Water boils, boiling water, at 1 atmosphere of pressure, 212 Fahrenheit, 100 degrees Celsius, or 373.15 Kelvin. And we could do the math here and figure it out. Okay, put 100 in here. All right, 100 times 9/5. 100 divided by 5 is 20. 20 times 9 is 180 plus 32, 212. Put 212 in here. 212 minus 32 is 180. Divided by 9 is 20 times 5. There's your 100 degrees. And then put your 100 degrees in here, and you get your 373.15. So these are your three formulas that you need. Here, here, and here. Or really it's 4 formulas, but these are really the same formula, just reversed. And that does it for temperature. All right, any questions on what we did today? We are done with Chapter 1. We'll be ready to start Chapter 2 next week. We'll talk about accuracy and precision at the beginning of next class. And I'll assign that. What I'll tell you is for this homework, 1.24 and 1.25, they just want you to write out the conversion factor. They want you to write out the factor label table. And just show how you would cancel the units. Okay, they just want you for 1.24 and 1.25, just write it out. There is no math to do so. Also, in 1.27, they use a term called angstroms. A with a little hat on it. The A with a little hat is 10 to the minus 10th of a meter. So you can use that for your conversions. Okay. So page 138, 1.24 to 1.44, that deals with temperature and conversions and all that fun stuff. 1.44 and 1.46, that deals with density, and there's other density problems. And then this group down here deals with sig figs, okay, and scientific notation.